Ladies and gentlemen, it's pleasant that the discussion is turning more active. Now we're ready to proceed the work, and let me give the floor to another speaker. Maglev technologies are mostly popular on transport, but not only transport. General Director of ThyssenKrupp Transrapid GmbH, Dr. Friedrich Loser, Munich, Germany, will tell us about the experience of maglev applications in other areas.
So I start. Honorable professors of this splendid university, dear students, dear colleagues, I would like to give an introduction to another maglev application, not only in the horizontal but also in the vertical. So I'm dealing with a new type of elevator system using linear drives and allowing to have multiple cars in the same shaft, the so-called multi-product. Just for the overview, of course, I will refer to our well-known product, Transrapid Maglev, give an introduction to the new system, and tell about the showcase. So we have really realized hardware, and then I give an outlook. So that's our well-known product, Transrapid. It's well, the main feature, contactless operation, of course, and on the other side, it's actually a mechatronic system. Mechatronic means we integrate mechanical items, electrical, power electronics, system safety electronics, and software into one system. And this is a key success factor, to have that integrated in one system. And on the right side, so we have the main items of online diagnostic as a key success factor, and an automatic train operation and communication system. So these are the core items. This is a must to have a maglev system operating, whether it's running in horizontal or in vertical. So this has already been shown by Professor Lin this morning, so I should not repeat too much. So we are running for about 15 years of operation, and just from the early beginning, our well-respected Chinese colleagues took over the responsibility for maintenance and operation. So that means such a system can be easily operated by any operator in the world. And the main feature is that we have a splendid diagnostic systems in the electronics. This is a key success factor. Now, let's go to the inspiration for the elevator business. So Transrapid features are applicable for elevator, so in terms of a synchronous linear motor, and a system architecture based on multiple autonomous electronic modules, an automatic operation control, lightweight construction, and a guideway based on elements with precise equipment. Just to compare Transrapid and the elevator system Multi. So the propulsion is a long stator linear motor, that's the same. For levitation in the Transrapid Maglev, we have levitation magnets, but in the elevator application, the linear motor itself keeps the car levitating. For the guidance in the elevator application, rollers are enough, and for parking brake safety, we have mechanical brakes in the elevator application. And at the end, there is an important small difference for the rating of the motor. In the horizontal operation, the rating of the linear motor is just to accelerate. But in the elevator, the rating of the motor is keep the whole weight of the car and accelerate. So that means lightweight construction is an important item for this product. And so what are the features for multi? What do we want to achieve? A key item of elevator is that we have an efficient use of space. In modern buildings, we are wasting too much space for elevators. And if there is the opportunity to have multiple cars operating in the same shaft, we can reduce the space demand for elevators and reduce the waiting times, because just in a railroad, cars are leaving on one shaft and arriving on the other shaft, and every few seconds a car can be leaving. Of course, safety is a must, and in an electronic-based system, of course, availability is a must. Such system must not fail. And to achieve that, we need a smart structure of autonomous components, redundant components, tolerating failures, including a diagnostic system to indicate defective units for the maintenance. So now I should start the video. Can you help me to run the... Yes, please. Okay, this is now first the advertising. Okay, so far that's on the next picture. Now I'm turning to the engineering side and are showing to you realized hardware in work. Could you please start again? Okay, so this is hardware in a test environment where you see the cars moving as well in vertical as well in horizontal motion, driven by a linear long stator motor. So this is a simple turntable electronics out of industrial automation application. So it's a combination of marketable components. There are no components specially developed or no system specially developed, all out of the market. And the smart issue, the challenge is a smart system architecture. So the benefits, what we can achieve is that we increase the transport capacity. So we can have multiple cars in the same shaft and need a considerably reduced mass. And at the end, we have a much smaller footprint in the building. So the expense in the construction for elevator shafts is significantly reduced. And that's what is challenging and fascinating, amazing for the architectures, is that there is no more restriction in the height of the building or in the shape of the building. Up to now we have the rope and pull up cars up and down. something like that. Now we are moving with several cars and have them circulated, running as well in vertical as well in horizontal direction. So that's more or less the history of the building. On the left side, the classical elevator, that we can put two elevator cars together, have two cars in the same shaft, and on the right side, that is the future of a multi with several cars in vertical and horizontal movement. And this is reality. The test tower in Rottweil, that's a small town in southern Germany, and there we have a big building, 240 meters height, and we have installed a test demonstrator, full scale, for doing the qualification and starting with the safety assessment work. And in that tower, you see here, we have installed what I showed before. So this is the principle. You can take out of the paper. This is the turntable where we can change the direction from vertical to horizontal direction of the car. This is the track. You can see the guidance system. These are conventional rails of elevator. And on the left side, you see indicated the linear drive elements, the linear motor, and the inverters, which are distributed along the shaft. So this is just a scheme of the power supply. The key item is redundancy. Any of the elements may fail, but we continue operation. High availability is a must for such a system. And this is just the principle. It's all very well known. What you see on the left side in the bottom is an energy buffer. We have performed successful tests with ultracapacitors, and they provide some benefits I show later. This is the motor. On the left side, on the bottom, you see the stator, small elements manufactured based on robotics, small elements put together in the shaft. On the right side is the arrangement of the permanent magnets, which are linked to the cabin. So this is just a picture to compare the effect of capacitors as an energy buffer without buffering. So we have high peak power from the grid when we accelerate and run up, and high peak power when we feed back into the grid. And by using capacitive elements, we can smoothen the power demand line to the grid, and this is an important economic factor in the equipment of the buildings. So for the conclusion, we know about Transrapid. It's successfully running. We have now another product for the vertical direction. It is commissioned, and the expected features were well proven. And what is now ongoing, entering in the market with an already defined launching customer, do the safety assessment and start with the pilot project. And so this is when looking to the modern mega cities in the future, we are providing smart solutions to provide solutions for transport demand in the large cities and between the large cities. So thank you for your kind attention.
Thank you very much. Maglev technologies are used in transport, on entertainment, or in industry. What are the advantages of this technology and commercial operation? Advantages.
The advantages of the technology in the elevator business.
In any commercial operations. Entertainment, maybe, industry, elevator.
At the end, it is the smart mechatronic solution. we solve mechanical issues by electronic elements and create lower operating cost and higher transport performance. So this is the key, using electronic means. And this is the same for all similar applications, and maglev is a core.
Thank you. Maybe Sergey Smirnov, tell me please, maybe you can see problems of this technology. I mean maglev inside buildings. What do you think about it?
Yeah, maglev in large buildings.
Yes.
Yeah. So
I can hear Sergey Smirnov.
Yeah. Yeah.
Frankly speaking, I see no big risks there. If the technology is proved, so it's okay. We can trust the company who implemented transplantation technology, tested and operated for several years, and there is no difference from magnetic levitation, horizontal or vertical levitation. That's technology nearly the same, and as for me, I welcome all the applications of maglev technologies. Because 100 years ago, for example, we had no ideas about what's waiting us in the future. But today we have so many technologies around us, and they started from computers and earlier from steam engines and so on. So we don't know what will be in the future, but I have a faith that maglev technology can lead us to the brighter future and for breakthroughs and for outstanding technologies for the tomorrow.
So, do you think it's some trend of or single engineering ideas?
I'm not sure it's a trend today, but I think in some years it will be.
Thank you. Thank you, Mr. Loser. Science is always on the move. Researchers on maglev technologies are continued. The president of Maglev Transport Incorporated, a member of the IMB, Lawrence Blow, Washington, D.C., USA, will give you an insight into the fresh ideas. Please, welcome.
Thank you. I'd like to start by thanking Sergey and all of the staff at the university for making this meeting possible. It's my first visit in the Russian Federation. Unfortunately, my luggage didn't make the trip with me, and that's why I'm so casually dressed. I need to say that out loud, just to let you know. I would like to report a report that will be very similar to one that I've made over the last 10 years. We've been talking about projects in the USA for a long time. And just out of curiosity, by a show of hands, how many people attended the International Maglev Board meeting in Berlin 2 years ago? 2 years ago. How about the program 2 years prior to that in Rio? Fewer. And before that, in Daejeon, South Korea? Getting lower. Okay. San Diego in 2008. How about that? Very good. Well, those of you that kept raising your hands, I think now you can check your email, because you're going to be seeing some very familiar charts for the next 10 minutes. It will be a rundown of that will be very familiar. And here's a summary, so there's no suspense. The activities in the USA for the last several years, especially the last couple, have been very discouraging, because they've been disappearing one by one. We've had changes at the federal level with national elections, and it seems as if our will to do big infrastructure projects like a maglev project would be an intercity project That will is fading. Now, the U.S. has gone through several periods of activity, followed by concurrent periods of inactivity. In the States, you could look at a period from 1965 to 1975 as a period of very, very intense activity. And from 75 until 1985, there was almost a vacuum of activity in the States. From 85 to 2005, the next 20 years, was a very steady series of studies, pre-construction planning studies, environmental studies, safety studies, all focused on putting a high-speed intercity maglev into place. And in the US, like the Russian Federation or China, we've got lots of land to work with. So we had lots of potential projects. And I'll talk about a few of them. If we talk about intercity, we really only have two candidates. Oh, I should say, these are the systems I'll be talking about: intercity high speed, low speed urban, as we've heard from several speakers before, and then other systems that are more innovative or research oriented. The high speed systems, everyone knows the two commercial grade systems, one from Germany, the Transrapid, that's been working in Shanghai with really good experience for the last 14, 15 years. And then the superconducting maglev from Japan that's still going along very steadily, headed to a commercial introduction in the next 6 or 8 years. In the USA, you can tell the strike-throughs. Those were some of the projects I was mentioning that had a lot of activity around them in terms of planning from the late 90s until the mid-2000s. These are all projects. There are 5 or 6 in a row there, all of which have withered and are now essentially dormant. There's only one, Baltimore, Maryland, to our nation's capital in Washington, D.C. It's about a 64-kilometer line that looked like an ideal first project for a Transrapid-style vehicle. It's the only surviving project, and now it has been overtaken and replaced by the same two city centers with the different technology coming from Japan. The superconducting maglev, which we heard about earlier today, is the target technology now for going between Baltimore, Maryland, and Washington, D.C. as the country's first commercial-grade maglev project. It's been working for 6 or 8 years now in the planning phases, and relations between Japan and the U.S. have been very positive. Prime Minister Abe from Japan came to the States 5 years ago and made a very attractive offer to license the technology and to donate, from what I understand, donate about $5 billion US to invest in the project's early phases. That was something that was started some years ago, and that continues to be the only real project that is active in the USA, high speed. That's it. They're now working to finish up their most detailed studies, environmental planning studies that include safety, noise situations, noise impacts, electromagnetic fields, all the classic environmental subjects. They're going through that. And at the bottom of this slide, you can see, it's maybe hard to read, but their current status, they're in mid-year 2018, they're going through what we call a, federal environmental impact study or statement. They should be through in the next, with these studies, they should be through in the next 2 years, and then there's a decision about 2 years from now whether or not to go forward to construct the system. On the other end of the technology extreme, we have the lower speed urban maglevs. There were 5 or 6 of these. I've faded out a few in the middle because the groups that have been pushing them have receded into the background. The first one, American Maglev Technology, is an urban system that's been running on a prototype test track for about 10 years. They have been planning, their most recent project that was planned was a system of an urban demo project with the 4-station run in Orlando, Florida, near Disneyland, Disney World out there. The project was recently replaced by a light rail project, and the magnetic levitation competitor or technology was disbanded or discarded. And as of today, as far as I know, there are no active projects in the U.S. or in North America for American maglev technology. Another one of the urban systems that's been around for about 50 years in studies is called MagneMotion. We heard from earlier from Professor Lin that there's an activity based in Shanghai now to do a hardware demonstration of this technology, which I think is terrific to keep it going, because the company in Boston, Massachusetts has sort of moved on to other things. They've taken their technology and gone away. They have sold, MagneMotion company sold their technology to another American company called MagPlane, which was a long-term urban system that's been in studies for another 40, 50 years. This MagPlane, the company, the corporate company, has got several initiatives now based in China to do a demonstration for a mining application using their motor technology. There are other cargo delivery system plans that are in place in China, and they're also looking at one of these very high speed, I think 600 kmh type speed maglev for China, and they are doing some sort of a development demonstration near Shanghai, which we've heard about for the first time this morning. Again, the company itself has moved on, and there are no projects in North America. There is a project in Canada, which is called Magnovate, a new late-breaking sort of a project. It's only been around for about 5 years. They're studying some very interesting technology, such as passive switching, permanent magnet, levitation, and lateral guidance. And they are looking to get a first demonstration in Toronto for, it turns out, for a connector in the Toronto Zoo. I hear that the decision to give them seed money is pending. That's the last I heard, pending. There are no projects in the lower states for Magnovate. I call these other innovative approaches because I don't really know what to say about them with respect to maglev. These are Hyperloop variants. Everyone, I think, has heard of Hyperloop or caught the Hyperloop buzz, so to speak. And embedded in just about every Hyperloop proposal that I've seen is a magnetic levitation subsystem of some sort. It's either a primary or a secondary system, but coming along with the Hyperloop is a lot of activity in universities and companies around the world. Maybe, is there a Hyperloop in the Russian Federation? I don't know. Is there a Hyperloop activity there? Here? No. Research, maybe? No matter, my personal opinion is I'm really glad that Hyperloop is out there, because young people all around the world are now catching some kind of a maglev buzz. They're getting an idea that magnetic levitation can be an enabling technology for a large-scale project such as Hyperloop. I don't know, I don't think anyone really knows what Hyperloop will turn into, but at some point it will involve a magnetic levitation subsystem. And I think that's a good thing. I think the best thing is that young people all over the world are excited, and that unfortunately is where things should be, in the hands of young people who don't know how hard the job is my point. And the last, in the lower right-hand corner, is another one of these innovative concepts. It's being run, again, by the visionary Elon Musk. He calls it the Boring Company, and it's anything but. It's a tunneling company that he has ideas about all over the country, one of which happens to be between Baltimore, Maryland, and Washington, D.C. It's not a competitor to the magnetic levitation project, but it could be a complementary thing, meaning he wants to put very high-tech tunnels with extremely high-tech vehicles running in them, which is the graphic there in the lower right. Again, it's a visionary type project. I don't know where it's going to go, but that's keeping some kind of momentum alive for magnetic levitation. Now, if you take the Hyperloop excitement and you overlay it on the North American continent, this is the kind of grid that you could make up. I've lifted this graphic from a consultant who's done a lot of thinking, and if you might not be able to see, but each, it doesn't work, each, oh, there it is. Does that not show? There it is. Each grid, each definition there along each one of those lines is a 5-minute travel, 5 minutes of vehicle travel between any of these two city points. For instance, Kansas City to Chicago, that looks like 1, 2, 3, 4, 5, 6. That looks like a 40-minute trip, which would be a terrific reduction in speed. It's unclear whether that means a concurrent reduction in energy use or noise or vibration or electromagnetic fields. Who knows? But the innovative concept comes in to overlay the country in projects such as this, and just about every node on that map has a group, either corporate or a university group, attached to creating a Hyperloop project in that area. And that's as much excitement as we can generate in North America, unfortunately. So to summarize, it has not been the most encouraging couple of years, the last couple of years. The economic outlook for large-scale projects is not that good. But there are these large-scale ideas that have captured people's imagination. And I think that all by itself, if you look at them, they're listed there at the bottom. The Northeast Maglev is the name of the Japanese project between Baltimore and Washington. The Hyperloop is whatever it is, and the Boring Company is the other innovative maglev derivative type project that's out there. And that's it for the North American continent for this cycle. Thank you.
Thank you. I know that USA Railway transport is mainly privately owned. Will it be the same with maglev? If yes, is this good or bad? What do you think?
Private ownership?
Privately.
I think it's impossible. I don't think it's good or bad. It's just not possible.
No.
There's too much money involved. I mean, if you need 100 million euros, I don't know how many rubles that is, but let's say 100 million euros per kilometer, if that's a requirement. Who's got the private money to invest in a project that's more than 10 kilometers long? I don't know. I'm not trying to be flip. I'm trying to answer your question. I think it's impossible.
Okay.
Maybe someone disagrees with me, but I don't know.
Thank you. The history of maglev in USA is decades. Somehow, it's similar to the European history. Does Europe or USA have more prospects in maglev? What do you think?
Are you referring to intercity maglev or the urban maglev?
USA maglev or Europe maglev? What do you think? Who have more prospects?
Well, both Europe and the US have looked at many potential projects, and neither country has one. The projects are in Asia, China or Japan. I think that's the story. Let's take Germany as a good example. In my mind, Germany is the best example of why there is no European maglev. Germany's high-speed rail system is so comprehensive and so well integrated into the society that a maglev is not required. It could have been between Berlin and Hamburg years ago. That was an ideal application for intercity maglev. But for reasons that are too complicated for this audience and for me as well as an American, it went away. And I've never seen, I don't think there's another project in Germany that will ever use the Transrapid technology. I hate to say that with my friend from Germany here, but the time has passed, I'm afraid. And in the US, we were looking at Germany as the example to bring a transrapid to the US. Now we're looking to the Japanese to bring their technology to the US. I just don't see the US or Germany. As I stand here now, this is my 30th year of doing maglev studies. I'm not proud of that, but that's a fact. And we have nothing to show for it. Now, you don't want me to weep as I tell you this, but it's really discouraging that the only thing we have to look forward to is to incorporate a project from Japan that is a wonderful project. But there's no American component. It would have been true with Transrapid as well, but we already had a plan for doing technology transfer. I know I've run out of time. I don't care. It's a hard thing to do, and we are failing miserably.
Thank you very much for your answer and your presentation. And good luck with our airlines. I'm sure your baggage will be okay. As a journalist, I often see many articles on passenger maglev systems. But what do we know about freight maglev? The main question is how the freight maglev development will influence the world economy. Please welcome senior researcher of the Scientific and Research Laboratory Transport Innovative Development of Emperor Alexander I St. Petersburg State Transport University, member of the International Maglev Steering Committee, Mr. Sergei Smirnov, St. Petersburg, Russia.
Thank you. Dear colleagues, dear guests, welcome to St. Petersburg. It is very nice that the discussions of maglev technology issues expand their geography, and it's very nice to see people here from all over the world. I think it is very important, and I would like to tell about the things that concern all over the world about maglev technology. I start with obvious things. First, I would like to tell, we spent a lot of time for this research, to make this study. And when we started, we expected to get very, very interesting results, very promising for magnetic levitation. We expected to have a real breakthrough that will help maglev. But when we were in the second half of our research, we found very interesting results, and until the last moment I was afraid if I can tell it for the wide audience. So anyway, I will tell the truth about maglev, about magnetic levitation, about its impact on economics, and then it will be a good topic to decide further what is good for the world economics and what is not, what consequences. So, I start with obvious things. There are 6 most widespread modes of freight transport in the world. All of those modes of transportation has its competitive advantages. All of them have their particular use. For example, if we are talking about pipeline transportation or conveyor transportation, there are specific types of cargo for the transportation. Sometimes modes of freight transport may be in some competition on main lines, on mainline transportation, and they also can integrate into multimodal logistic chains. So, it is not dependent on which mode of transportation we use, but we have the transportation infrastructure. There are classically 4 main groups of this infrastructure. 2 of them concerns cargo transportation itself and cargo storaging. And 2 other groups cover the support of the technology and maintenance. So, with the use of those modes of freight transport and this infrastructure, we shape the logistic chains. You can see at the picture the most widespread logistic chain. So, of course, the shape of a chain may differ. It depends on the location of start point and end point, on the characteristics of cargo, on infrastructure development in current region. But I marked green the items of these chains, the echelons, which are always used. We have a start point and end point and door-to-door transportation. Very often, we have a mainline transportation. But if we turn to logistics, what's the issue? What's the main issue of the logistics? Last mile. Last mile logistics, it's a science. There is a special method to calculate the last mile logistics. It's the very complex problem. But mainline transportation usually considered as a local problem of one infrastructure company, which actually is not true. Such attitude caused by classic approach to economics of freight transportation. So, what we have in the economics of freight transportation? We have traditionally cost centers. We have two groups of effects, additive effects and multiplicative effects. So, what we have there? The main transportation expenses appear at transportation units, at infrastructure, and taxes and different payments concerned all those things. So, additive effects concern the extensive factors of transportation costs. So, the core idea is that the transportation chain cost is the sum of its stages. So, the cost of a stage is influenced by its main characteristics. For transportation echelons, it's distance, of course, and for storage echelons, it's the period of storage. Multiplicative effects are far more interesting. They have different nature and have an interest rate as a core. Those effects have more serious influence on end product cost. For example, 1 month transportation interest rate may cost up to 0.5% of cargo cost. It's a significant amount. At the next stages of distribution, after the transportation, interest rates raise up, as well as value-added tax. So, and this leads to increase of end product prices. And those effects, multiplicative effects, and its influence on end product cost are in the focus of our research. So, this is the configuration of transportation market. It is a wider approach than I shown in the very beginning. We can see the market in a wide view, and the number of market participants consists of different groups. So, the first group, there's a regulatory frame which determines the market development and operational activities. Of course, there are more functions on this frame, but now I will not focus on this. There are shippers and receivers, who are, of course, the essential part of transportation market. And there are 3 other groups which are in focus of the research. You can see it. It's logistic, maintenance and support, and manufacturing and construction companies. Their interests are very complicated and they are in a very tight link. We found that those groups have the crucial influence on the economics in a whole. This is the simple picture, simple map of interest at the transportation market. It is drawn as simple as it is possible. I made it very, very simple. We can see from this picture there are the relations between market participants concern the infrastructure, rolling stock, and resources and raw materials. What we see from this picture, the interests of operation companies on one side, rolling stock operation companies and infrastructure operation companies, and interests of maintenance companies, manufacturers and suppliers on other side are opposite. There are 4 actual conflicts concerned: A, infrastructure sustainability. Infrastructure operators are interested in. Infrastructure maintenance companies do not. Rolling stock availability, rolling stock life cycle, and the 4th one, the quality of resources and raw materials. There is also one potential conflict concerned infrastructure expansion. Infrastructure companies are interested in infrastructure they require accordingly to their prospects, to the cargo flows, to the traffic, but the companies who construct and build infrastructure, they interested in as large infrastructure as it is possible. So, all the conflicts are the point of compromises, of course, where companies find the agreeable balance between the sides. But the rest sides are not involved in this process. And despite the regulations, despite the regulatory bodies try to protect other market participants, they feel the transaction costs. So, next simple picture, the economics of interests. What we see there? We see some very unpleasant things. End product cost is determined by a group of different, linked with each other costs. We see the multiplicative effect which appears in maintenance and supplement. Each transportation echelon cost includes costs for different types of maintenance, including return rate of maintenance companies. Maintenance costs include costs of raw materials and resources, including manufacturers' interest rate. And cost of transportation includes transportation companies' return rate. So, there are many things which determine the growing of end product cost. So, of course, the transportation expenses are not the largest part of end product self-cost, of course. But it may cause its appreciation for some percent, which may be significant. So, from the first glance, the described situation has a negative impact on the economics. But, as I said at the very beginning, further investigation showed that the situation is far more complicated. Of course, transport, as we know, plays an important role in a gross domestic product. We hear it from TV, we read it in the newspapers, and we try to draw a picture how it is important. Okay, let's start from some definitions. Now, let's start from figures, and then from definitions. As we can see, the share of freight transport in GDP may reach 25%, which is serious. Transportation costs may reach 10% of product prices. And the transport itself consumes up to 25% of produced energy. So, the effectiveness of freight transport should affect the effectiveness of economics. The key question is how. And here we switch into definitions. There are two tightly linked definitions: economic growth and GDP. Traditionally, the economic growth could be called as a mirror of GDP growth. At the international level, it is, of course, the sum of national GDPs. If we are talking about the GDP, there are three approaches how to calculate it. That's income approach. So there we consider national income, depreciation, indirect taxes, and minus 2 items. There is expenditure approach, where we're talking about consumption, investments, government spending, and net export. And the production approach. So you can see it at the bottom. If we calculate the GDP using 3 different approaches, it is not a secret that we will have the same result. So let's pay the attention to the items of different approaches and link those with the picture of economics of interest. So we discovered a very specific situation. The ineffective from the point of transaction cost system leads to GDP growth. We have the increase of national income because salaries and maintenance and manufacturing corporate profits of companies involved in those sectors. We have their investments and we have high depreciation. Second, we have a consumption growth in terms of prices and increase of investments. And we also have clear GDP growth from production approach. The negative side is a lower quality of economic growth, but who cares? Usually, no one say about the quality of economic growth. Usually, we hear only the figure of the economic growth. So, we all know about characteristics of maglev transport, especially interworking between infrastructure and rolling stock. Accounting for those, we considered the impact of freight maglev on interests of transportation market participants. As it was expected, some participants win, but others lose. So the winning is for operation companies, as they have more sustainable infrastructure, more sustainable rolling stock, and they don't need a huge rolling stock. But maintenance companies have lower demand on their services first, and they have no opportunity to earn much from wearing of the infrastructure and rolling stock. So, changes in the conditions lead to the question, what is the real impact of freight maglev on GDP? We think we found answer on these questions. As we see, we have only 2 positive effects and 5 negative effects. It's sad, but we can't measure the positive effects. The measurement is challenging because we have a quality of economic growth which has no conventional scale. And it's very tricky, calculation of decline of intermediate product consumption. On the other hand, we can calculate negative effects. We have clear statistics. It could be calculated easily up to euros, cents, dollars, rubles. Any currency, there are statistics. And the negative impact of maglev transportation on GDP and economic growth could be easily calculated, while the advantages are not obvious. So, there is no clear answer. Is the cumulative effect positive? Unfortunately. And this applies not for freight maglev only, but for passenger maglev and any other maglev system. Nevertheless, the summary of impact can be made, and it is a bit more optimistic than the previous picture. It is seen that the picture, this real picture, is not as frightening. For example, in long-term prospect, we can expect the expansion of consumption. It is very important. Of course, the different indicators show decline, and many countries fight against this decline from year to year. But as we know, the chaos has a creative element. And in our case, we believe the chaos leads to the diversification of economics. And there's one more important thing that is missing here on this picture. The ecological debt. Modern economic system cares little about resources, but the Earth cannot provide the economic with all the necessary resources. Today, we live as we had 1.7 planets. It's too much. You know, have you ever heard about Earth Overshoot Day? This year, it was on August the 1st. It means that by the 1st of August, we consumed all the resources which the Earth can provide us for the 1 year. So, the ecological debt is growing up every year, excluding the years where the economic crisis was. So, and at the right side, you see some examples of ineffective resources consumption and transport. I focused on railway transport. There is a huge loss of resources. The first figure applies to EU. I tried to calculate, but I checked Deutsche Bahn and CNCF timetable and lost count. Next two figures apply to Russia. And unfortunately, railway transportation, modern railway transportation, leads to waste of resources, and the amount of resources is not limited. And on the other hand, we have low coefficient of efficiency of different modes of transport. That means that the rest percentage from those figures is wasted resources, and we do not have a serious potential for changing the situation. So we made the conclusion that we need a new attitude to the economics itself. So, as a conclusion, I would like to say a couple of words about the history. I hope we all know the history and we learn lessons from the history. We had some technological revolutions and industrial shifts. All those led to growing the productivity and decreasing of the labor force use. Maglev is in the trend. The world is very dynamic and it changes more or less dramatically. We can see it in economics, in technologies, in the environment, and so on. And the development of freight maglev is in this trend, but its implementation requires changes in our attitude to economic and world around us. And I would like you to ask yourselves, are you prepared for different attitude? Thank you.
You've just told us about the conflict of interest between service companies and macroeconomics problems. How can we solve this problem?
No, I'm not sure it's solvable at the current moment. Service companies anyway will decrease their business because of maglev implementation. But when there's a wind of change, it is a good idea to build a mill, but not the wall. So they should find different areas where to do business. So I don't know if there are different solutions.
For what planning horizon this analysis conducted? Were the planning horizons iterations conducted?
Sorry, may I repeat the question one more time? It was a bit noisy.
Repeat?
Yeah.
For what planning horizon was this analysis conducted? And were the planning horizons iterations conducted?
It's not an easy question. No, I think this is the point for further investigations, for further investigations, and unfortunately at the current moment we are nearly alone at this topic. And I would like to call other members of the scientific society to join us and to research different things together.
Thank you for your interesting presentation. We have heard today of many maglev systems, but high-speed railways are also actively developing today. So we've got maglev at one scale plate and railway transport and the other. One technology excludes the other or not? I think it's a very interesting issue. The floor is given to the head of the Department of Railways, the Institute of Railway Technology, Dr. Sven Korner, Dresden, Germany.
Thank you very much for the introduction. Maybe one topic is actually a little bit missing, and I hope in my presentation I can pick up this topic, and the topic belongs to a technical side of view. So I would like to give you a presentation about the key underlying technologies for high-speed maglev. And as you see maybe in the picture, I would like to show you this based on the German development of the transfer pit. Here in the picture you see the transfer pit 09. This was a vehicle which was originally planned to operate in Munich, but due to the cost increase, it was not built. Before I start, we are just a small company, and just let's give me some words to my company. We as an independent engineering consulting company solve technical solutions. And our expertise is shown on the presentation, but we are qualified to speak here because we were involved in almost all feasibility studies for the German transfer pit projects as well as for international projects. That means we made the design and the layout of the traction power supply as well as the propulsion system. And our company was also involved in the approval of the only commercial transfer pit project in the world in the Shanghai. So our company has made the approval for the propulsion technology in Shanghai. When we have a look at on the future challenges of an increasing population and the resulting challenges in transportation, then we can define some trends. First of all, we have an increasing population, especially in cities. Thus, especially in China, but also in Russia, we have the creation of megacities as well as metropolitan regions. We call it metropolis. We have also an increase of transportation needs. And also, megacities require sustainable and environmentally friendly mobility. Thus, we need concepts to keep the cities, of course, alive. We have also requirements for higher speeds, shorter headways, and an increasing transportation capacities, which means the operators are required to provide more couverture on in the railway wagons as well as on the car wagons, etc. And thus, we have a need for efficient and powerful electrical transportation systems. When you have a look at the pictures on the left-hand side, you see some pictures of actual developments in Europe. So actually, our car developers like Volkswagen, Audi, Daimler, BMW, trying to find the shift from a combustion engine towards electrical propulsion systems. Another aspect, this is a picture in the middle, is that we try to electrify our highways. Due to the increase of freight transport over the next years, we see that is required to look for new technologies, and the electrification of these highways is one trend. And the last picture represents the new ICE4 high-speed train, because high-speed systems occupy an important place in future mobility. When we now go a little bit back in the history, and remember the issues why we in Germany started the development of the high-speed maglev systems, then we need to have a look at the technical and economical operating speed, or its limits, of high-speed rail. And this is decisively influenced by the rolling process between the steel wheel and the rail. You have point or loadings on the point, and thus causes, of course, a lot of wear. You have limited axle loads and weights you can operate on the railway tracks. In Russia, you have broader gauge or wide gauge, and thus you have higher axle loads, but also these are limited. You have all the emissions of noise, which will influence, of course, people living close to the high-speed lines. You have the ground vibrations caused by conventional railways. You have also the issue that you need to take care of the safety and braking technology. Everything must be safe. No one wants to have any injuries. You have also the fact that you need the guidance and derailment safety. And not at last, you need to take care about the power transmission. If you want to drive fast, you need to install the power anyhow, either on the locomotive or along the track. And the limiting factor when you drive fast is the power transmission between usually the contact wire and the pantograph. The next thing is that when you want to when you want to drive fast, you need to overcome the driving resistances. And you need to have a look on the power and energy demands. The last three issues are highlighted bold because I want to make some explanations on this. When in Germany the development starts in terms of the transfer speed, we had one goal. The first goal was that the train levitates from 0 speed, so already at 0 km/h up to the maximum speed. This was the first goal. And the second goal was that the power transmission is completely free of any conductive transmission systems. So we want to avoid the pantograph as well as any contact wire. Let's start with the small power demand at the beginning. The approach is that you want to have a contact-free onboard energy transmission, and thus the linear generator was invented. The principle of the linear generator is highlighted in this slide. In the lower part of the picture, you see a supporting magnet which belongs to the vehicle. This supporting magnet has an excitation winding, and this winding creates the magnetic flux for the suspension of the magnetic vehicle. On the upper side, you have this trackside starter package, just as a schematic. And thus, you see the linear generator winding is located in the supporting magnet. And due to the Maxwell law and due to the movement of the vehicle, you can decouple a voltage out of the exciting field. This is rectified with some power electronics on the vehicle and then used for the onboard energy. The negative effect is, due to the principle of the linear generator, you will get a driving resistance which belongs to the linear generator, and the driving resistance is higher at lower speeds. This, usually the linear generator is used for higher speeds, let's say starting at 70 kilometers or even 100 kilometers per hour. To overcome these disadvantages, ThyssenKrupp invented a couple of years ago the contact-free inductive power supply for a power transmission also at low speeds from 0 to almost 70 kilometers per hour. This principle, which is shown here, is basically or is based on high-speed inductive power supply. This is the same principle which are today used when you want to load your mobile phone without connecting an USB plug or something like this. It works with higher frequencies of up to 20 kilohertz, and you will get, of course, much more power over this IPS system. When we now leave the low power demand and shift to high power demand, I would like to have initially a look at the high-speed railways in Germany. The high-speed railway development started with the ICE1 or with the ICE2 up to the newest generation of ICE4 trains nowadays. And when you have a look at the configuration, you see the first two series are based on power cars. That means you have electric locomotives. The ICE3 and ICE4 actually have distributed power cars. That means you need to install much more power, but the space where you can install the power in a motor is limited due to the gauge and due to the free space in the locomotive or in the electrical multiple unit. And when we have a look at the maximum electrical power at the pantograph, which is drawn usually by these locomotives, we see that we have two power cars, ICE1 of approximately 11.5 megawatt, 6 megawatt for the ICE2, there's only one power car, and so on. And you also see the related speeds. And now the question is, what is the idea behind the slide? When we have a look at the air resistance of the transfer pit, especially here for a 4 section and an 8 section, we see that we have quite high aerodynamic resistances which need to be overcome by the motor. The motor power which is required is handed on the right-hand side. You see values of 20 megawatt or even 30 megawatt or even more, in dependency of the speed. And when you remember the last slide, you see, okay, there is no space to install such much power. And thus, we need to ask, how can we overcome this driving resistance, this pure physics, to achieve speeds of 500 or 600 kilometers per hour? So, for high-speed operation, it is required to overcome the aerodynamic resistance, which is proportional to the speed, to the square of the speed. And in general, you have three possibilities. The first possibility is that you reduce the drag. This is conventionally done in almost all systems. That means you have influence on the aerodynamical design of the vehicle front, the configuration as well as the shape of the entire train. The second approach is to reduce the air pressure. This approach is actually investigated by the Hyperloop companies, or the German approach is just to install this power. And thus, the restriction by mounting space on bogies and motor input voltages in the locomotives leads to the development of electrical multiple units with distributed propulsion systems. And for even more power, the solution is a long stator linear motor. And this is the same approach like the Japanese use. It's also a synchronous motor. The one is with iron, the other is without, but it doesn't matter. When we now have a look at the propulsion system, we see that the long stator linear motor has a power supply and a propulsion. Due to the configuration of this long stator motor, we are required to separate the stator sections. And you can imagine when you have a small electrical background, when you have a high power demand from an electrical network, it will cause high voltage drops. These high voltage drops need to be handled, and this is done by the separation of the stator sections. And the next key technology was the development of the double end feeding. The double end feeding means that the propulsion segments are fed by two traction substations, which are far away, up to 50 kilometers. This is a quite challenging technical solution, because you need to consider when you, I don't know whether you have ever dealt with semiconductors, but when you have two active converters which have a distance of almost 30 to 50 kilometers, you need to synchronize converter 1 and converter 2 in such a way that the resulting current is exact in the amplitude, phase and frequency you want. And this is quite challenging. Here, because I'm an electrical engineer, I can't, or I need to show an equivalent circuit diagram. This is just the basic principle of the double-end feeding. As when you deal with high frequencies, you need to consider, of course, not only the time dependency of voltage and current, but also the position dependency. That means the regulating control to propel the maglev vehicle. This model is much more complex. This is just for the student layout to demonstrate, okay, what are the general dependencies. When we have a look at the propulsion system, we actually see that those elements which are actually built stationary are also used in locomotive. When we start with the main transformer, it is not a three-phase transformer, but a one-phase transformer for high-speed railways. For the magnetic levitation systems, we have three-phase transformers as well as three-phase main converters. So it's the same elements which you will find also on a locomotive. When we look at the propulsion, especially at the red element, the limiting factors in history were the motor converter and the power of the semiconductors in combination with the motor transformer. We have to overcome these physics, and these physics are nowadays also possible to overcome with the development of modular multi-level direct converters. When we would have a closer look on this topology, we already see that there are three-level converters used. When we now want to increase the speed with higher frequencies, with higher powers, we need much more of this concept. These modular multi-level direct converters are already actually built for stationary railway traction power supply systems. We have in Germany, for instance, the world's largest converter station. It works as a networking coupling between the high voltage railway grid and the traction power supply level of 15 kV. And there a power of 450 megawatt are installed. So this is absolutely scalable from low power demand up to high power demand. Thus, I would like just to summarize the main key underlying technologies. First of all, we wanted to avoid the connection, contact wire and pantograph. This can be done with the linear generator as well as the inductive power supply. And for the high power demand, the German approach was to implement the long starter linear motor and to develop the double end feeding. For this double end feeding, we have also much more key underlying technologies, like the synchronization of the drive control between adjacent substations, also the electromagnetic levitation, and for the synchronization as well, the powerful data transmission. If Russia has any questions, I think we can answer them, because there's an available product which is not been successful economical yet, but it's possible in future. Thank you for attention. And ja želaju vam mnogo interesnoj prezentaciji na konferenciji. Ja živu vas, всего хорошего.
Thank you. You've told us about different technologies underlying the maglev systems. What do you think goes next? Will technology platforms come closer to each other? or will the diversification be broadened?
So I think when we just focus on the high-speed maglev, then first of all, the technologies are already close together. We have long starter synchronous motors in Japan. It's a different approach to the earthquakes which will occur in Japan, so it's a complete different safety basis compared to the German approach. In general, when we have a look at these semiconductors, there are huge developments. The developments belong to higher voltages, higher currents, and higher power. Especially in Germany, we have companies like ABB, General Electric, and Siemens, which are, I think, quite famous in the world in developing semiconductors and semiconductor applications. And these companies, of course, lead the process to a platform. We see it already in the conventional railway system, where we have such standard converter units. So you can, usually the minimum unit is a power unit of 5 megawatt or 5 MVA, and then you can scale it concrete to your defined project. So you can scale it from 5 megawatt up to 50 or even up to 100 or even more. So the platforms will in future, of course, come closer together.
Thank you. What technologies do you think are the most universal and commercial justified?
Well, I think the German transfer as well as the Japanese technology are, when they show their commercial success, quite challenging. From my point of view, the highest challenge when you develop a new system is the way to achieve the approval. Somewhere you need an authority which will tell you or give you the stamp to say, okay, you are allowed to operate with people. And thus is the most important challenging thing. And there we have two products in the world, either the Japanese or the German system. And I expect the Chinese system, which Mr. Lin showed us today, I think is also on the right way. It's similar to the transfer system, and I think also the Chinese will achieve a product which will be approved by authorities. And thus is the basic, for the operation, for the later operation.
Mm-hmm. Maybe our experts have any questions to Mr. Corner? No? Thank you very much for your presentation. Now our plenary session has come to an end. We have heard quite a lot of opinions. I think the discussion was productive. It's good if other questions spring up. That means we will meet more often. I think the entire world has come to a conclusion that we cannot do without maglev, and we know how impressive many projects are. Japan, China, South Korea. Maglev is being developed in other countries, including Russia. This means sooner or later we will all start traveling faster, more comfortable, and safer. The number of skeptics is falling, and this is good news. We're not through with the discussion today. Now is the time of sectional meetings, but before, a few words of gratitude. Many thanks to our sponsors. You've been very helpful. Many thanks to Strush Group of companies, manufacturer of highly accurate blocking and sealing devices for a wide range of application. The company Belt Transservice, the biggest private operator specializing in railway transportation of oil cargo in Russia, CIS and Baltic states. And let me remind you that all participants can proceed working in sections after a short break. The topics and speakers are specified in the program. The participants are invited to discuss the reports. Thank you for your attention. Bye.